So this week you'll find that the slideshow and the Chapter 5 activity have a lot of the same questions. So I will point out to you in this slideshow when the problem we're doing is actually on the activity. So get your activity ready, print it out if you have a printer. Otherwise, have a notebook handy for writing down your work for the Chapter 5 activity as we're going through this. So last week we learned about discrete random variables. Now we're learning about continuous random variables. So do you know the difference between discrete and continuous? Discrete are things that we count, so we'll have numbers like 0, 1, 2, 3. And continuous, when you're measuring things in grams or in inches, you could get a decimal. So the heights of these radish plants are continuous random variables. Makes me remember that I have some radish seeds I need to plant. So is each of these random variables discrete or continuous? This is on your worksheet. The distance to work, that would be continuous. In miles, it might end up being a decimal. So that's going to be continuous. Your height in inches would be continuous. The number of earthquakes in a given year is going to be discrete. And the number of heads, if you flip a coin, is discrete. Now, random variables are variables that take on values, but it's a little unpredictable which value they'll take on. However, in math, we know that there's different likelihoods for different values of the random variable. And the probability distribution answers the question. This is on your worksheet. What is the likelihood? The probability distribution answers this question. So a discrete probability distribution gives the probability that a discrete random variable takes on a particular value. This is a graph of the binomial distribution, and the probability of success is 25%. There's your P, your probability of success. And this is telling us that they're doing 20 trials. So it can't be a coin flip because it's not 50% success. So it would be some other experiment where there's 25% chance of success and you do 20 repeated trials. So the most likely outcome is that we get 5. Maybe this is a spinner. And I'm just coming up with this on the fly. And the spinner would have 4 sections, and this would be the success region. And then this would be failure, failure, failure. But 25% chance of success. And so if you spin this spinner 20 times, X would be the number of times you land on success. Out of 20 spins. So the most likely outcome is that you end up landing on success 5 times, which makes sense because it's 25% of 20. And if you look here, you can see the height of this is just slightly bigger than 0.2, which makes me want to check what is that actual number. So I could go to my calculator and do binom PDF 20, 0.25, 5, and I'm guessing that that's going to come out to be 0.21 or really close. And I don't want to hold you up while I type that in, but double check that and see how close I was. And of course, we see that the probability of getting success 11 times is pretty low. So this is just a discrete probability distribution. Even though you don't know the outcome of the experiment, you know that a 4, a 5, or a 6 are pretty likely outcomes, and a 1 or an 11 are pretty unlikely. Okay. X is the number of successes in 20 trials if the probability of success is 25%. X is distributed binomially with the parameters n and p, n comma p, so 20 comma 0.25. All right, you know what? I'm going to go put this in my calculator. Binom PDF 20 comma 0.25 comma 5. And let's see what we get on that. Second distribution. Oh, it's 0.2023. So it's not even 0.21, but it is slightly bigger than 20%. And then what is the probability that X is less than or equal to 5? So now we want to add up all the probabilities for 5, 4, 3, 2, and 1, and 0. Add up all of those, which we could do, or we can just do binom CDF 20 comma 0.25 comma 5, and that's going to be higher because we're doing all of those probabilities added together. And I am getting 0.6172. So we can round both of these to 2 decimal places. This would be 0.62. This would be 0.20. So that's just a review of a discrete probability distribution, and we are getting ready to segue into a continuous probability distribution. And when it's continuous, we don't have these little segments. That's for 4, that's for 5, that's for 6, that's for 7, and so on. Continuous means that we can have decimals. So instead of having what looks like a histogram, we have a curve that could look like this. So I still have the values of X, the possible values of X here. And we don't know which one we're going to get. And then we have the probabilities here. So the probabilities for this one start off kind of low, get higher around 5, and then go back down again. And this distribution is slightly skewed to the right. But all of the values of X are possible. Like we could look at this graph for 5.13 or something like that. So here I'm making up an example. I'm saying that X could be the prices of used cars in thousands of dollars. So we could say that this is a $20,000 car here, less likely, more likely a $5,000 car. Maybe this is the likelihood that I'm going to buy a certain car. As it gets more expensive, I'm less likely to buy it. What is the probability that X is equal to 5? Well, one thing that we're going to learn in these continuous probability distributions is that we're looking for areas. The probability of a car costing exactly $5,000 is actually pretty low. So the area shaded is 0. This is totally different than discrete probability distributions, where we would go up and then we would just read where we are on the graph. It's pretty unlikely that you go out and buy a car and it costs exactly $5,000. It might cost $5,200 or $203 or something like that. So that single probability is 0. Next, let's shade the area for the probability that the car value is less than or equal to 5. And again, I'll just write that down because I know that some of you forget which way the inequalities go. X is less than or equal to 5. Okay, so we're going to shade that region in the diagram. And we have no idea how much area we just shaded. That is going to be something we'll use our calculator for. But right now we're just happy that we shaded it. I would guess that that's less than 50%. I'd say maybe 30 or 40% likelihood. We can't really read off of these numbers for the area. So let's just write a note, sorry about that. Write a note that says probability is area. Probability is area, or the area is the probability that we're shading. So what is our interpretation here? Well, the probability of having a car, or of me buying a car that costs $5,000 or less, is about 35 or 40%, I'm guessing. And again, don't worry, we'll get into more precise methods where we're not guessing. But I can tell that less than 50% of this area is shaded.